Okay. So I believe the last time we stopped at the infinite. Let's check it.
Infinite line charge, sir.
Right. Let me make sure. This one, right?
Yes, sir. And then we did some, then the video, some examples.
Okay.
Oh, sir, I had a question about one of the questions that I did, sir. I wasn't quite sure how you derived the formula that I use in DS.
You want to leave that for 2 o'clock?
All right, yeah, all right, yeah. Yeah,
so
that's yeah.
Sorry. Still can't get rid of this cough, brother. Okay. Now, Maxwell has 4 equations. Anyone who ever come close to the topic of electromagnetics, it's a must that you know Maxwell's equations. In other words, there is no problem in electromagnetics that you cannot solve if you are familiar with Maxwell's equation. As a matter of fact, if you ever have to do a oral exam or an interview, obviously you're under pressure, you don't know the solutions. The only good place to start is with Maxwell equation. I can remember, because in the United States, when you go for a job interview after graduating, they usually have a whiteboard and a problem, and they send you to the board to solve that problem. And I can't forget when I went to the interview with Intel, and they sent me to the board to solve the problem, the electromagnetic problem. The way I started, I said, I'm going to try to think through this problem, but according to Maxwell's equations, I'm going to write down the 4 of them and we see what I have in the problem, and then I start from there. And they say, sit down, you have the job. So make sure whatever you do, you learn Maxwell's equation. Well, you have learned one already, but we're going to put it in a compact form for you. So, the divergence theory. The divergence of electric flux density D is given by integral over the closed surface of D dot ds. As the limit goes to 0 is equal to this. Now, This is a mathematical expression. So just like differentiation, that's what divergence is. The differentiation of a vector. All right. The way we went through and explained differentiation, this one is not as simple. So the like how in the mathematics class they ask you to accept that dy dx of x squared is nx to the n minus 1. At this point, I'm going to ask you to accept that the divergence of d is equal to this. But let's look at it a little bit.
Wait, sir, quick question, sir.
Mm-hmm.
If this is for the rectangular plane, right, sir? So if it was in like the spherical plane, sir,
Yes.
why would be okay?
Yes, it would be different. It's different. And if you look in the appendix of any electromagnetics book, these are some formula that are listed for you. And any exam would give you like the divergence in all the coordinate systems. So you wouldn't have to worry about remembering them or deriving them. But let's recall from Gauss's law. Q flux equal charge equal the integral over the closed surface of d dot ds. This is your total flux. And you recall that?
Yes, sir. Yes, sir.
And on a per unit basis, all you have to do is divide by the volume. So if you take a very small volume, limit as the volume goes to 0, right? This is rho v at a point. Which is the volume charge density at the point where divergence is obtained. So what all this is saying is del dot d, which is the divergence of d, equal rho v. So what is Maxwell's first equation? This is volume charge density around a point. The equation 6 is called Maxwell's first equation applied to electrostatics?
Sir, is that a bar above the V, sir, or is that like an arrow?
Above D?
For me. Yeah. I won't know V, sir. Oh, no, sorry. It's a triangle, my bad, sir.
Is del dot. This is your symbol for del. Divergence of D equal rho V. So this equation 6 is called Maxwell's first equation applied to electrostatics. This is also called the point form of Gauss's law, or Gauss's law in differential form.
Wait, sir, can you scroll back up a second, sir? Let me just take a quick. Thank you, sir.
Okay. Okay. So another two mathematical expression that I want to introduce you to. From Gauss' law in the point form, which is del dot D equal rho V. Poisson's equation can be derived. So look at this again. Del dot D equal rho V. D is the flux density, and rho V is the volume charge density. We know that D equal epsilon E. So this is just follow it's mathematics. Just follow the mathematics. So D equal epsilon E. We know that from before. So we're gonna substitute the epsilon E for D. So del dot epsilon E equal rho V. Right? Now, we also know that E equal minus del V. So we're gonna substitute minus del V for E in here. So we have this. Epsilon is a constant. So we're gonna take it outside. So we have del dot, I would take the epsilon and the minus outside the bracket. So we have del dot del V. And we're gonna divide over here your mathematics by the epsilon. All right. So we have del dot del V equal this. Del dot del is del squared. So del squared is this. This equation is called Poisson equation, named after the mathematician that did this work. Now, remember, rho v is your volume charge density. So if you're ever in a region where your charge density is 0, then del square V equals 0. And this equation is called your Laplace equation. So Laplace equation is a special case of Poisson's equation where there is no charge in the region. Any question?
Sir, my only question right now is like how this exactly work into the questions.
Huh?
As in, sorry, so like what exactly is the divergence of the charges, sir?
Pass that item, man.
Okay, sir?
When I pass that, I never stop me up here. Ain't that the first thing I do, not this video? What the divergence is.
Oh yeah. Yes, sir. Yes, sir. Thanks, sir.
Okay. Okay. So now, remember at the beginning of the course, we said that every aspect of electrical engineering has its roots in electromagnetics. Now, we're gonna start looking at that now. So let us just read through this for a minute. Current and current density. You know, current is defined as the rate of flow of charge and is measured in amperes. A current of 1 ampere is said to be flowing across the surface when a charge of 1 coulomb is passing across the surface in 1 second. So you put in your ammeter, and it says the current is 1 ampere. You know that 1 coulomb is going across whatever the conductor is in 1 second. The current is considered to be the motion of the positive charges. The conventional current is due to the flow of electrons, which are negatively charged. Hence, the direction of conventional current is assumed to be opposite to the direction of the flow of electrons. Read that over until you get it. Any question? Okay.
No, sir.
No, sir, just 1 second, sir. I mean, you can keep going, sir. Sorry.
The current which exists in the conductor due to the drifting of electrons under the influence of applied voltage is called drift current. So we are talking about 2 different currents. See if you can differentiate between them.
So the drift current would be as a result of conventional current. Is that what you mean?
No. You have conventional current. Right?
Yeah.
And you have drift current.
So what do you mean by drifting of electrons? Like
Wait.
move from positive to negative, negative to positive. What do you mean by that, sir?
All right. If you have an electric charge, right? You will have an electric field. Right? Now, the electric field lines are a result of the electric field, which are electrons. So if you put your ammeter in that path, it will register current. But there is no conductor that these electrons are flowing through. Yeah, that's a good way to explain it. the conventional current, which we so rename, you have to have it's flowing in a conductor, right? Now, when you have an electric field in a space, you have electrons crossing that space, causing field lines. But you don't have, so if you have electrons passing through, this results in current. You don't have any conductor. So we say this current is a result of drifting of electrons.
Sir,
It's drifting in space, not flowing through the conductor. Yes.
so would the drift current be like what happens in a PN junction? Sir?
No, the PN junction.
So wait, so sir, you say it's completely different from conventional current and then the first current that we're talking about. So you mean it's like current that happens when just voltage is happening like the general area, like it's not happening in this conductor per se, but it's happening close by, so the current is going to drift.
Right. Let me see now. Okay. It's like people say them don't want a cell tower beside them because radiation, right? Radiation from the tower give them cancer. There are some truth to it, because if you have a source of charge, right? Remember, the field lines generating from that charge terminate somewhere. Right? So let us for a moment consider the bar magnet, right? Where you have your north and the south. Right, so you have these field lines, right? So these are a result of charge generating from one end and terminating on the other. In this field, you have current, right? But you don't have a conductor per se. So if you put your meter here to measure what's going on there, it will show you some current, right? But there is not, but you don't have a conductor.
And that current is going to be the drift current, sir.
That's drift current. So you have a current that flows.
Respect, sir.
You have a current that flows under the influence of electric field.
Is that so? Would that be like acceptable explanation, sir? Just the back current, the backflow of current within a conductor due to the effects of electric field, or due to the effects of the applied voltage.
I didn't get that. I didn't get that. Come again.
Like because you say the current is basically going back in a way because of the voltage source.
No. All right. Look at it this way. You have a current. All right.
Yes, sir.
If you have a circuit and you have a voltage source, which is a potential, you have a potential difference. So say your voltage source is 10 volts, right? And you have a resistor, you connect it with wire. Right? Because of the potential difference between the two ends, a current will flow through the wire. So the current that flows through that wire is called a conventional current. At the same time, if you have 2-point charges in space, right? You have electric field lines from one terminating on the other. These field lines are a form of current, but they are not flowing through any conductor. That's the drift current.
Oh, I think well,
So
just to
yeah.
clarify, sir,
Eh?
just to clarify, if we like drop a conductor in them path now, that drift current is going to start affecting the conductor.
It don't be drift current no more, sir. That'll be conventional current, right?
If you do what?
We put a conductor.
Yeah.
So if you have a conductor that the flux lines go through, it wouldn't be a drift current.
Oh, okay. I get to know, sir. I get to know, sir. So, yeah, I get to know.
Okay. All right. So the current which exists in the conductor due to the drifting of electrons under the influence of an applied voltage is called a drift current. While in dielectric, there can be flow of charges under the influence of electric field intensity. So, such a current is called.
Oh, wait, sir, before you continue, sir, I wanted to clarify something in that sentence. It said under the influence of the applied voltage. Should that be under the influence of electromagnetic fields? Because that kind of
I
confused me.
think they mean like if I apply like a DC source, like a battery.
Send me to that sentence.
The one that will just come off us, sir.
This one?
Right above. No, right above it. Right above it.
This one?
Yeah, right there. Yes, sir.
The current which exists in the conductor due to the drifting of electrons under the influence of applied voltage is called drift current.
And it says here that we get drift current when there is no conductor. So what I'm wondering is, if instead of applied voltage, then they mean electromagnetic field.
What that means is that made up in your current, made up in the current that you are measuring. You see, what we did earlier was we decouple them, we set them apart to explain what is drift current and what is conventional current. Now, in your circuit, when you are measuring, and that's why you have things like the covering on your wire, right? So what that does is it captures both your drift current and your conventional current within the wire. So what you're measuring is a combination of both.
So it's just not cut out, so what the point here?
Okay. Then restart. All right, let's give it a little patience, and we'll see. It will soon become a little bit clearer. So while in dielectrics, there can be flow of charges under the influence of electric field intensity. Such a current is called displacement current or convection current. The current flowing across the capacitor. Yeah, there is your example. The current flowing across the capacitor through the dielectric separating its plates is an example of convection current. The analysis of such currents in the field theory is based on defining a current density at a point in the field. The current density is a vector quantity associated with the current and is denoted by J. So current density is J. All right. Read from here to here, read that over and see if it makes sense to you.
So an easy way to look at it here is like the current that occurs due to the displacement of electrons, like in a capacitor.
Remember, in a capacitor, you have two plates, right?
Yes, sir.
So you don't have a conductor
Between them.
between these plates. So somehow the electrons have to cross the insulator, the whatever dielectric you have between the two plates. Right?
Yes, sir.
So if the electrons move across, and that's a current.
Oh. Oh, so it's the current that managed to make it across this the space, the dielectric between them.
Exactly. So that is your displacement current. All right. So now, we know what is I, and we kind of know what is J. What is J again?
The current density.
Vector for current density.
The current density. So we know what is I and we know what is J. But let us really know what is J. Consider a surface S. Here's a surface S. Right? And I is the current passing through the surface. The direction of the current is normal to the surface S. And hence the direction of J is also normal to the surfaces. This is gonna be very important. That means your blasted current no run so. In normal to the surface at right angle, right?
Good. So you see now, repeat. So J was the, sir?
Hmm?
You said J was the current vector?
No, density. Current density.
Okay, thank you.
So, before we go through what am I gonna go through then? So, this is your J. This is your current, right? So, current is your J that's normal to the surface. So if you capture your current density here, you have to resolve it in a normal component and a tangential component. All right, I know so you know me, I go. So what we are going to reach for now? You tell me which formula we're going to reach for.
The one for surface area, sir. Charging a surface area.
Hold on. So DS is DS normal. J equal J normal. So we're gonna reach for the vector calculus, the vector algebra. because J dot ds, the differential current DI passing through the differential surface ds is given by the dot product of the current density J. So we have your direction vector, right, which is the A normal. So if we have an expression for the current density, right, and we are only interested in the normal component for the current. So the dot product of J with the normal will give you that current going there. So DI equal J dot ds. Because the normal component of this is the same direction of this, so the angle cos theta is 0. So J dot ds will give you the value of the normal component of J. So your total current I equal the integral over the entire surface of J ds. So you get current from EMT. Thus J is in amps per meter square and ds is in meter square. Then current obtained in amperes A.
Sir, can go up a bit for a few seconds? Just a little bit.
Go back up.
Yeah, just a bit, sir. Yeah, right there.
Sir,
Yeah.
and can you assign vector J for any of the four currents you described, sir? For analysis?
For any of the four currents,
Yes. Is it that J is only for when you're dealing with conductors, or you can consider it for other currents?
no, J is the current density, is the total current. So it can be a combination.
Okay.
Wait, sir, so it's possible if J is not normal, it's possible for I to be normal and J to not be normal?
Now, if J is not normal to the surface, it can be resolved into a normal component and a tangential component.
Any chance you can go back again real quick, sir? I didn't see that part. Just the last part. I did not end. I didn't see.
Let me answer that other question. This is J, right?
Yes, sir.
So we're gonna resolve it into a normal component, a tangential component, right?
Oh,
Pythagoras, right?
oh, yes, sir. All right, I'm get that. Get that.
Because remember, J is a vector.
So it have the angles and such.
So this normal component, when you dot it with the direction, you get the angle between it is 0. So cos theta is 1. But when you dot this with this, the angle is 90, so cos theta is 0. So if you dot this at any time with the direction of the surface, all you get is the
It's
normal
zero.
component. So,
Okay.
get it?
Yeah, yeah, I get that point. So you can just pause on the calculations when you reach it, sir, at the end. A bit more. Yeah. Thank you, sir.
So the relationship between J and rho v. The set of charged particles give rise to a charge density rho v in a volume. The current density J can be related to the velocity with which the volume charge density, that is, charged particles in the volume, crosses the surface S at a point. This is shown in the figure. The velocity at which the charge is getting transferred is V. That is your velocity. Your charge is going from here to here. It is a vector quantity. Velocity is a vector. To derive the relationship between J and rho v, consider the differential volume delta V having charge density rho v as shown in 5.3. So here is your delta V, right? So your delta Q, which is the total charge in your small volume, is rho V, which is the charge density multiplied by the small volume.
Sir, what is the small volume? Oh, no worries, sir.
Okay. Now delta V is length time width, delta S, no, the surface times the length. We are dealing with a cube. So delta Q cube Q equal rho V delta S times delta L. So we are going to say the charge in the X direction, which is velocity, we're gonna denote it Vx. Delta I is the rate of movement of charge. So and delta I is the charge crossing the surface, delta S. So delta I is delta Q over T. And we already established that this is delta S. So delta Q equal this. Just follow that maths.
So who did you say you sent this document to distribute it to the class, sir?
Just follow the thing, no, man. You know, it's been
Yes,
taped.
sir, but yeah,
It's
screw,
been
sir, so
taped. It's been taped. Don't I send the thing to you, man?
I didn't get it, sir.
But you get the tape for the class, them, and this is on the tape. You go over them?
Yes, sir, that's how I got the last note, but I was just
Okay.
looking
Well,
forward
just
to
if you get the last note, you will get this too, and it's there. Good learning is not always the easiest way out, man. Where was I? Okay. So I was saying, just follow this mathematics. So let me see. Next, we want to do the continuity equation, right? But so when we come back, we're gonna do the continuity equation. No, okay. Those 2 hours are for us to work some problems. But I really want to spend 20 minutes out of it to finish up conductors. Let me see if we'll be able to do it. All right. We're gonna leave it. All right, when we come back, we're just gonna do continuity equation before we jump into some problems. So we're gonna start here when we come back for half an hour, and then we do the examples. All right.
Sir, no problem, sir.
So when we're coming back, 2 o'clock or 3?
2 o'clock, sir.
2.
Yes, sir.
4.
2 to 4. Okay, cool.